Hello everyone, and welcome to the module on local NVMe storage and the block volume service. After completing this lesson, you should be able to create, attach, configure, and mount block volumes, backup and restore block volumes, understand block volume cloning service, and be able to differentiate between block volumes and boot volumes. As a quick storage primer, it's important to understand the various storage options, especially when evaluating against what a customer might have in their on-premises infrastructure. First option, DAS, or Direct Attached Storage. In a data center, this would be direct attached storage or local disks that are physically within or physically attached to the underlying physical compute resource. SAN, or Storage Area Network, provides connectivity to storage resources via block-based protocols such as FC, or Fiber Channel, FCOE, or Fiber Channel over Ethernet, or iSCSI. Storage resources are presented to hosts as SCSI logical unit numbers, or LUNs. Think of a LUN as a raw disk device that looks and behaves exactly like a local disk. The host OS or hypervisor formats the LUN and writes a file system to it after it's attached. NAS, or Network Attached Storage, provides connectivity to storage resources via TCP/IP-based file sharing protocols such as NFS, SMB, or Samba, or CIFS, also known as CIFS. Storage resources are presented to hosts as export and shares. The hosts do not need to write a file system to the mounted volume, as the file system already exists. Simple iSCSI SANs. In an iSCSI SAN, initiators read and write the data requests to the target over an IP network. Initiators and targets are technically processes that run on the respective devices. We refer to compute instances as the initiator and the iSCSI storage device as the target. An iSCSI target is usually either a server with lots of disks attached or a storage array. Every device on an iSCSI SAN needs a name. Most common is IQN, or iSCSI qualified name. What we have following there is an example of an iSCSI name. As we evaluate the different storage options available within OCI, it's important to understand some of the key benefits of the different storage options. If we start at the top there with lowest latency, we'll find that the local NVMe storage is going to be the lowest possible latency available from a storage medium. These are non-persistent, high-performance, local to the compute instance. They're ideal for big data, online transaction processing, and other high-performance workloads. Just down the list would be block storage volumes. They are persistent, durable, and high-performance storage devices. Ideal apps that require storage area network-like features and performance would be ideal for block storage volumes. The major difference here is that local NVMe is, of course, direct attached, whereas block volume storage is presented over the network. These local NVMe devices are all solid-state drives. Some instance shapes in OCI include local NVMe by design. The local NVMe solid-state drives can be used for workloads that have high storage performance requirements. Local attached SSDs are not protected, and OCI provides no RAID, snapshots, backup capabilities for these devices. However, the customer may opt to implement their own data protection solution in the form of RAID. One key difference between Oracle Cloud and other cloud provider SSD or NVMe storage is that the Oracle local attached SSD drives are persistent. With competitors such as Amazon Web Services, that local attached storage is considered ephemeral. If you stop an AWS compute resource, all local storage is automatically eliminated. With Oracle Cloud, with OCI, if you stop a resource with local attached storage, that storage persists and is available once you restart that compute resource. In order to protect against physical device failures, a customer may opt to implement one of the following RAID configurations. With RAID 0, or mirroring, we create an exact copy of the data across two disk drives. Then, in this case, if one disk drive happens to fail, the data persists on the other physical drive. With RAID 10, we use a series of mirror drives to create a RAID stripe. And what this does is, on the first set of drives are going to be mirrored in RAID 1, and then we stripe all the data writes across 2 or more RAID 1 sets. So each block gets written to the first RAID 1 set. That block is then replicated across 2 physical drives. Then the next block or the next bit is written to the second set and the third set and so on down. This not only gives us faster performance, but we're also able to sustain one physical device failure across each one of those RAID 1 sets without compromising our data. RAID 6 is a block level striping with 2 parity blocks. So in this instance, we would have 2 of the available drives dedicated for parity, meaning we could lose up to 2 physical drives without losing any of our data. The NVMe local attached storage does come with a service level agreement. This is measured against 4K block sizes with 100% random write workload on the dense I/O shapes where the drive is in a steady state of operation. As you can see there with shapes like the BM Dense I/O 252, we guarantee a minimum of 3 million IOs per second. That's incredibly fast. The block volume service lets you store data on block volumes that are independent of the compute resource. They persist beyond the life of any given compute resource. Block volumes operate at the raw storage device level and manage data as a set of numbered fixed size blocks using a protocol such as iSCSI. You can create, attach, connect, and move volumes as needed to meet your storage and application requirements. Typical scenarios for this would include persistent and durable storage, the ability to expand the storage of a given instance, or scale the capacity of an existing instance. Some key features of the block storage service. Currently, the volume sizes can range from 50 gigabytes up to 16 terabytes. The disk performance is all solid state drive under the cover. So there's no spindles, there's no moving parts, they're all solid state. In terms of performance, we designed the system to allow for 60 IOs per second per gigabyte, up to 25,000 IOs per second per volume. So at about 400 gigabytes, a single block volume would deliver 25,000 IOs per second. That's going to give us about 480 kilobytes per second per gigabyte, up to 320 megabytes per second of total throughput. With a single instance, we can attach up to 32 block volumes, giving us about half a petabyte of total storage. This gives us, in particular configurations, also up to 400,000 IOs per second with a single compute resource. Now, the block volume service itself is durable by design. So a single block volume includes multiple replicas across multiple storage servers within an availability domain. And as we've seen with many other services already, the data is encrypted at rest and in transit. If we restore from a backup, it takes less than a minute regardless of size. We'll talk about that in a bit more detail, but that's an incredibly fast performance for recovering or creating new block volumes, and then they're available almost immediately for use. In terms of backup performance, it takes about 30 minutes for 2 terabytes or so. So the amount of time required would be more or less depending upon the amount of data stored on a block volume. The different block volume service components include an instance, which is our compute resource, our host, iSCSI, which is that TCP/IP based standard for communication between the instance and the attached volume, and then the volume itself. While the underlying infrastructure is essentially the same, we do differentiate between block volume and boot volume because of the capabilities of these two different devices. A block volume is a detachable block storage device that allows you to dynamically expand the storage capacity of an instance. Block volumes can be attached and detached to a running instance and will persist beyond the life of a compute resource. A boot volume is also detachable. However, the host must be stopped before the boot volume can be detached. And the boot volume can also be used to create a custom image that can then be used to create additional compute resources. When we create a boot volume, we are going to specify the compartment, the name, the availability domain, and the size. We also have the option to select a backup policy. These backup policies, which we'll talk about in a few more slides, give us the ability to automatically back up the data on a regular recurring basis without any additional customer interaction. When we choose the connectivity type, when we mount this block volume to our compute resource, we have 2 options. We have iSCSI, which we've been discussing. This is a direct attach over the network to the host. So once that volume is ready for use, we would log into our compute resource, issue a series of iSCSI commands, and the volume would be available for use. There's also the option to attach using paravirtualization. This is a light virtualization technique where the VM utilizes hypervisor APIs to access the remote storage directly as if it were a local device. When an instance no longer needs or requires a block volume, we can disconnect or detach that from the instance without any data loss. Again, if we wanted to reattach somewhere else, we could do that. When you reattach to another instance, however, there's no need to format or recreate the file system. The existing file system, the data, all persists. If you were to partition or create a new file system or otherwise format that drive, all data would then be lost. When the volume itself is no longer needed, we can simply delete the block volume and we're no longer being charged for that. Just be mindful you cannot undo a delete operation. If there's any chance that the data might be needed sometime in the future, it's always the best practice to create a manual snapshot before deleting the block volume. Backup is a complete point-in-time snapshot of your block volume. Backups are always encrypted, and they're going to be stored in the object storage service. They can be restored as new volumes within any availability domain within the same region. So while a single block volume, again, is availability domain specific, once we take a snapshot of that block volume, we could use that snapshot to create a new volume with the same data anywhere else in that region. There's two backup options. One is on demand, either via the management console or the CLI or the SDK. We can initiate a point-in-time snapshot. Alternatively, or in addition thereto, we can schedule automated backups to happen on our behalf. They're automatically scheduled and retained based on the selected policy. So a bronze backup will do monthly incrementals retained for 12 full months, plus a yearly full backup that's retained for 5 years. So if the data is not changing frequently, a bronze level backup might be sufficient. If you're working with applications where the data is changing more frequently and your recovery point objective might be lower, silver or gold may be more realistic. So silver would be a weekly incremental retained for 4 weeks, plus monthly incrementals, plus a yearly full, and then gold would be daily incrementals, plus weekly incrementals, plus yearly fulls retained for 5 years. On-demand one-off block volume backups provide a choice of incremental versus full backup options as well. So those incremental backups are going to be significantly faster as only the blocks that have changed since the previous backup would be collected. You can restore a volume in less than a minute, as we discussed, regardless of volume size. So when we go to restore a volume, it essentially creates that volume. It establishes what we call a block map, where all the bits exist, and it's available almost immediately for use. Now, as that volume is being utilized from the onset, we perform a feature or a task known as hydration. So behind the scenes, we're replicating all the blocks into place so that that volume becomes complete and whole. Now, it doesn't mean that you can't use the volume. Everything is available. All the data is there. You can read, you can write. It just takes a little bit of time for all of the data to be fully refreshed or fully hydrated on the underlying volume. As of this training, as of this recording, there's no backup feature for OS or operating system disks. However, if you needed to, you could create a boot image or a custom image of your boot volume. Cloning allows you to copy an entire existing block volume to a new block volume without having to go through the backup and restore process. Cloning is a point-in-time, direct disk-to-disk copy of the entire volume. The clone operation is immediate. So when we initiate the clone process, a new volume is generated, similar to when we execute a restore, and it's available for use in less than a minute. Then behind the scenes, we perform that same hydration task, and it takes about 15 minutes per terabyte to rehydrate that volume. But again, you can use the volume immediately, you can read to, and you can write from that volume as soon as it's available to mount to a host. A clone can be created within the same availability domain, and there's no need to detach the source volume. We can initiate a clone. It takes a one-time, point-in-time snapshot, and then hydrates the data in place over the next period of time. A clone can be attached and used as a regular volume when its lifecycle state changes from provisioning to available. And again, this is usually in less than a minute. Currently, once again, there's no option to clone an OS disk or change the block volume size when cloning. Boot volumes provide remote boot disks that are encrypted, have faster performance, lower launch times, and higher durability for both bare metal and VM instances. With these remote boot volumes, we have the ability to preserve your boot disk by keeping it after you terminate the compute resource. Similar to block volumes, these boot disks are highly durable because we create multiple replicas across or within the availability domain. Compute instances can do scaling via boot volumes, and what this means is if I needed to change the shape of my compute resource, I could terminate the existing instance and preserve the boot volume, then use that boot volume to launch a new, larger shape. With these remote boot volumes, we get faster launch times for both Linux and Windows VMs. And then all boot volumes are going to be encrypted by default. Being that these are remote, detachable boot volumes, it also gives us the ability to troubleshoot and repair our boot disk at the OS level. Very common task or very common troubleshooting step if you happen to lose SSH access to a Linux instance would be to stop the instance, detach the boot volume, attach the boot volume to a different compute resource, and mount it to the file system. You could then evaluate such folders or such files as authorized keys. You could check the permissions, make sure that SSH is configured and functioning properly, restore any missing SSH keys, then simply detach that boot volume, reattach it to the original host, and start the host back up. With boot volumes, we can also launch another instance. So if I've terminated a compute resource but retained that boot volume, I have the ability to, at a later date, simply select that boot volume when launching a compute resource, and it will create a new instance with that same OS and configuration as before. Boot volumes are only terminated when we manually delete them. And you'll see if you go to terminate a compute resource, there's a checkbox that says, would you like to also delete the boot volume? By default, that checkbox is not selected. So if I'm in a hurry and I terminate a compute resource and I forget and I just hit OK, that boot volume will persist. Boot volumes cannot be detached when the instance is running. We've talked about that. The boot volumes can be attached to an instance's block storage in order to debug issues. We can have custom boot volumes as mentioned in the compute module earlier. So being able to specify anything from the default, which is 50 gigabytes for Linux or 256 for Windows, all the way up to 16 terabytes, depending upon our requirements. In terms of pricing for block storage, it's a flat fee regardless. So it's 4.25 cents per gigabyte per month for provisioned capacity. So Oracle doesn't have the ability to see what data is stored, that it is encrypted, it's accessible only to the customer. So when the customer needs 400 gigabytes of space, we allocate that amount of space and we charge the customer accordingly. If they provision 400 gigabytes of storage and they put 1 megabyte of data on that storage, we're still charging for the 400 gigabytes. Now the benefit here is truly the cost for performance story. If we provision a 400 gigabyte volume, which gives us that maximum of 25,000 IOs per second per volume, the customer is going to pay $17 a month. If we compare this against the provisioned IOPS option with AWS, with their elastic block storage, we're getting 60 IOs per second per gigabyte, whereas with AWS, the maximum performance is 50 IOs per gigabyte per second. Now the other side of that is with provisioned IOPS on AWS, there's an additional charge for that performance. So not only would the customer pay 12.5 cents per gig per month for the storage, which is about $50 for that 400 gigabytes, they're also going to pay 6.5 cents per IO provisioned. So in this example, for a 20,000 IOPS drive at 400 gigabytes in size, the customer would be paying $1,350 per month with AWS. That means the same or better performance and similar storage on OCI is 79 times cheaper than it would be on AWS using their elastic block storage. So we looked at non-persistent, high-performance local NVMe storage. We took a look at the fact that local NVMe storage is good for big data workloads, online transaction processing, and high-performance workloads. We looked at the fact that NVMe storage is not durable. It does persist for reboots and stops, but as physical drives are prone to failure, the customer would need to implement their own protection using something like RAID to stripe the data across multiple volumes. OCI provides a service level agreement for the performance of these local NVMe drives. We also offer persistent, durable, high-performance block volume service with industry-leading price and performance. These block volumes can be used for workloads that require any sort of SAN-like performance, databases, Exchange server, web applications, anything that requires low latency, high performance storage. You can create, attach, connect, and move volumes as needed to meet your storage needs. The block volume service allows backups, both on-demand and automated, and you can use cloning to do a point-in-time direct disk-to-disk copy of an entire volume. And again, that disk cloning process makes the new volume available in less than a minute. Thanks for joining us. We'll see you at the next module.